Chapter 17, slides 1 through 3. In this chapter, we're going to be focusing on the word aromaticity, what it means, and how to predict it. Now, as I mentioned, benzene is an aromatic ring. And we're going to learn a lot more about what this means. But before we do anything else, and since benzene is what I'm going to be working with for the most part for the next chapter onward, I wanted to take a moment to talk a little bit about the special terms that we use when naming benzene systems. Benzene is probably one of the most prevalent aromatic rings, in nature, out there that we have to make as part of materials or pharmaceuticals. So I just wanted to take a moment to discuss some of the nomenclature as it pertains to IUPAC naming, and also common names that unfortunately have stuck around despite IUPAC naming, and what you should be aware of that you're going to be seeing a lot. So the relationship of substituents off of the benzene ring is what we're going to focus on. So here we have a benzene ring. Okay, it's a 6-membered ring with 3 pi conjugated bonds. When you have 2 groups, and it doesn't matter what those groups are, when you have 2 groups off of the benzene ring, when their relationship is 1,2, so this is 1,2 dichloro benzene. Okay, that's the IUPAC way of saying it. Now, whenever you have 2 substituents, they don't even have to be the same substituents. When you have 2 substituents that are in the relationship of carbon 1 and carbon 2, basically right next to each other, this is called ortho. Sometimes chemical companies, when selling products, will actually call it orthodichlorobenzene or simply orthochlorobenzene. So it is good to have an idea about this relationship, even though it's not technically IUPAC naming. Also, the thing to note is the fact that I didn't have to use the dichloro. I could just say orthochlorobenzene, and the fact that I'm telling you it's ortho means that there must be 2 of them. So it's not as, I don't think, as intuitive. It's much easier to read a 1,2-dichlorobenzene name than it is to, have to remember ortho. But the term ortho, if you're ever giving a presentation, you could say these ortho substituents, meaning these 2 substituents on the ring that are right next to each other. So you can use it as you're describing something in, say, a presentation. The second one is the meta positioning. This is simply a 1-3 relationship for the substituents. This is called meta. So when 2 groups are meta to one another, they're in a 1-3 relationship. This allows us to also shorthand some of these benzene names. So this would be a nitro group and a bromo group. So this would be 1-bromo, 3-nitrobenzene, or meta-bromo-nitrobenzene. I still prefer naming it 1-bromo, 3-nitrobenzene. I prefer the IUPAC system, but it is important, like I said, to recognize that meta means a 1-3 relationship. The last one is called para. You have a substituent here and a substituent here. And as I mentioned, this allows you to sometimes use a shorthand term to describe the name of the system. So yeah, we would call this 1, right? You've got like 1, 2, 3, and 4. You could say, or you could name it 1, 2, 3, and 4, right? So you could say 1-fluoro, 4-methyl benzene. But if you'll notice, having a methyl group on your benzene ring, this has an actual common name called toluene. So 4-methyl benzene can be shortened to toluene, and you can say parafluorotoluene. You actually don't even need the numbers because para tells you what the relationship is. They're exactly across one another, 1,4 relationship. And you have a fluorine and toluene, the methyl is worked into the common name toluene. So that's why you guys have been using in lab derivatives of benzoic acid. You could have metachlorobenzoic acid. What about metachloroperoxybenzoic acid? Here's a chlorine. And here's a meta position. Remember when you guys were talking about MCPBA, when we were epoxidizing double bonds? The M stands for meta. Metachloroperoxybenzoic acid. So they used sort of a grouped common name for the rest of it. But now you can go back and look at that MCPBA and understand that the M stands for meta. So to sum it up, ortho is when two substituents off a benzene ring are 1,2. Meta is when they have a 1,3 relationship. And para is when they have a 1,4 relationship. Okay, so what do you call that? That's a metaphor. How about this one? I could go on and on. I got so many of these. This is a paradox. Get it? See if you can make your own up. All right, so that's just a little bit about naming benzene. I really want you to get the ortho, meta, para in your brains so that when you see it out there in the jungle of chemistry, you'll go, oh, I know what that means. All right, how about the stability of benzene? Now I'm going to go back to conjugation, and I really want to hit home and drive the point to you guys how stable benzene is. I really want you to appreciate the stability of benzene. If you remember at the end of the last chapter, we talked about a benzene ring does not react with any of the standard alkene reactions that we studied in previous chapters. It's too stable. So how stable is it? Okay, let's start with a cyclohexene ring. When the cyclohexene ring is hydrogenated, they recognized that negative, so if you hydrogenate it, understand this is, we'll call this energy the energy of cyclohexane. Okay, so the baseline is cyclohexane. Understand that the drop in energy when you hydrogenate, you release negative 28.6 kilocalories per mole. Okay. If you multiply this by 2, it gets you roughly to where you're going to see 2 double bonds hydrogenated, right? So if you multiply 28.6 by 2, you get 57.2, negative 57.2. So remember that when you have 2 double bonds that are conjugated, it's not going to be negative 57.2. It's going to be a little less than that. And that's exactly what we see. We see negative 54.9. So it is more stable than the calculated doubled negative 28.6. Right? Okay, so you take negative 54.9, add another 28.6, and you get 85.8. Negative 85.8. I should say add another. It should be negative 28.6 times 3, right? If you have 3 double bonds. Now, it's not going to be just slightly less than 85 because if you think about it, the third double bond that you're adding is not just conjugated to the one, it's conjugated in both directions. So they did a calculation and they calculated that you're going to get about negative 78.9, so even more conjugated stability for 3 double bonds. So we should see a release in energy when hydrogenated to negative 78.9. You want to know what that's calculated, okay? Calculated. You want to know what we saw? Experimentally, 3 triple bonds in a benzene ring is more stable than 2 double bonds in a benzene ring. Isn't that nuts? Think about it. The drop they saw was negative 49.3 instead of the calculated negative 78.9. That is far more stable. So something else is going on here, and this is what, perplexed scientists for quite some time. We now know what these are. We know how to predict them. And it's an extra word that we can attribute. It's a special type of conjugation. So you can say to me, aha, these 2 double bonds I've just drawn are more stable because of conjugation. But when we're talking about a benzene ring, we actually don't use the word they are conjugated, yes, but we don't say, oh, things aren't happening or are happening because of heightened conjugation. We're going to switch now to a very special, very, very, very stable type of conjugation called aromaticity. And that's what this chapter is about. How to predict when a ring is aromatic and when it's not. I've drawn the benzene ring with its p orbitals shown and how they're all aligned and sharing the 3 pairs of electrons, the 6 electrons around and around and around that ring. So resonance around the ring of electron density allows for this extra stability. And the word aromatic has changed over time. Originally, a lot of these compounds smelt really nice, and so that's why the term aromatic came to pass. However, this term now means something very, very different. So what does it mean now? What does the word aromatic mean now? We know it means extra stability in these ring systems with high conjugation, but are all highly conjugated rings aromatic? And if I know that if I deem it aromatic, then I know it's super stable and it has certain properties. If not, it probably behaves just like a double bond, a non-conjugated system. So let's figure out how to look at rings and determine if they have this special, extra special superpower called aromaticity.